Hello viewers, welcome to CEC lectures. Myself Dr. Preeti Tagwani. I am an associate professor from Department of Computer Science, Aryabhat College, University of Delhi. So in this a series of advanced data structures and algorithm, presently we are learning the topic of deletion in B trees. And deletion, as I have told you, there can be three cases, as we have also seen different cases in the operation of insertion. Here we will be looking into various cases of deletion. So the first and the simplest case of deletion was when your key which is to be deleted is available at the leaf node, and even after deletion no property is going unbalanced. That means no or the node is actually not resulting in an kind of underflow situation. And here is an example. Let us take a quick recap and we will be moving on to our next cases. So here deletion of 32 is not going to violate any of the property. Deletion of 32 is immediately done, the simplest case. Now let us say we want to move on to the next sub part of the first case. Now the next sub part says we need to delete 31. The moment we are going to delete 31, it is going to trigger an underflow. In this situation we will start from left to right and try to see whether the sibling nodes are in a situation to give away a key. So here if we look into the left sibling, there are two keys 25 and 28. So one key can be borrowed from the left sibling, but it cannot be borrowed directly because otherwise it will disturb the search property of the B tree. If I am directly going to replace 31 with 28, that that can't be done. So 28 will be given to the the node which is the parent node. From there 30 is to be borrowed, or from there we can say the median key of 28, 30 and 33, which is 30, is to be borrowed, and this is what the situation is going to be. So 28 is given to the parent node, and from there 30 is going to be borrowed. So the final tree after the deletion of 31 looks like this. Now for example, if we want to have one more deletion in this situation, and that is nothing but the deletion of 30. Now see the if we are going to delete 30 immediately, then the node containing 30 is going to trigger an underflow. Now the idea says you start from left to right, and then you kind of start borrowing the key from the node which is in a situation to give away a key. Now starting from the left of 30, the node is having 25. So if it is going to lend 25 to the node with the key 30, this node itself will get into an underflow situation. So what I am trying to say here is left sibling is not in a situation to lend away a key. Similar situation is with right. Would have been there would have been two keys with the right, which is maybe let us say 35 and 37. We would have borrowed one from this the right sibling also. But here in this situation both the keys or we can say neither left nor right are in a situation to give away the key. So what is to be done in these sort of situations? Then a merging situation will occur, and this merging is to be actually done with the parent node. Now how are we going to do it? So the situation is both the immediate siblings left and right as well as right already have a minimum number of keys. Then what is to be done? Merge the node with either the left sibling node or the right sibling node, but the merging is done through the parent. Why this is to be done through the parent? In order to maintain the search property of the B tree. If merging is done directly, then search property cannot be cannot be maintained, or we can say if merging is done between the siblings directly without getting involved the parent node, that such property, we cannot, we can say, we cannot maintain. Now let us see how it is going to be done. So the situation here is, we have, I am just considering the the tree, the subtree which is of concern to me. So we have a parent node which is 28 and 33, and we have 25 on the left. In between 28 and 33 we have 30, and on the right side of 33 we have 35. Now what do we need to do? We need to remove 30. So both this immediate left and right we cannot borrow. So we need to merge these nodes. How this merging is going to happen? This is the situation. 30 is being deleted. Now with that, 25, which is on the left side, is going to be merged with the parent node, which is having 28 and 33. So 28 we are actually, kind of, we can say, borrowing, or we are descending down, and we have 25. So along with 25 and 28 we have one key. So 25 along with the key which is 28, and it has been taken from the parent, that is being, kind of merged, and we have formed one particular node consisting of 25 and 28. So would not have been this merger only, 28 and 33. For example, I am assuming that I am going to keep 28 there only. So for two keys we at least need, 3 children. So there was a shortage of one children. That in that situation what we did is we borrowed one key from, or we descended one key from the parent. Now there is only one key which is left on the parent, so it can have 2 children. So 2 children, and we have already the left and the right sibling were on the minimum threshold. So we have, just merged the key which is descended from the parent, which is 28, with the key which is, available on the left of that the concerned key. Now it is, the key, the situation is like 33 on the parent, 33 in the parent node. On the left we have 25 and 28, and on the right we have 45, and this makes our tree, sorted in terms of number of keys, number of nodes, also in terms of, its search property. That is also kind of, we can say, balanced. Now this was the case where we have seen two subparts. The case was the deletion, the deleted key, or the key which is to be deleted, lies on the leaf node. So the one case was underflow is triggered, another case was underflow is not triggered. So we have seen both the situation. But in my previous lecture I have told you that deletion is actually a complicated scenario as compared to insertion, because the key which we want to delete may lie on the internal node also. So this comes as our case 2, where the key to be deleted lies in the internal node. Now what are the sub cases which are going to occur with this situation? Let us see them, and then we will, try to understand with the help of figures and so on and so forth. So the internal node from which key is to be deleted will be replaced by in an in-order predecessor if the left child has more than minimum number of keys. So left child is having more than minimum number of keys. We are going to take one, key, and we are going to replace the node with the in-order predecessor. The the internal node, for example, can be, if we are going to, delete an internal node, it may be replaced by in order successor if the right child has more than minimum number of keys. So in order successor is to be taken from the right child if it is having more than minimum number of keys, and in order predecessor is to be taken from the left child if left child is having, surplus number of keys other than minimum number of keys, whatever the threshold is according to, the value of m. Now in that set situation also, if either the child has exactly a minimum number of keys, then merge the left and right children. That means none of the children is in a situation to kind of give away its in order, the corresponding in order predecessor and successor. Then so the situation is, if either child has exactly a minimum number of keys, then we can merge the left and right children. But after merging, if the parent node has less than minimum number of keys, then we need to look for the siblings of the parent, as we did in case 1. So, now let us try to understand the situation in a comprehensive manner. What are we trying to do? So, the situation is, we are trying to delete from internal node. So, whenever internal node I am talking about, in order successor and in order in order successor and in order predecessor come into the picture to play their role. So, internal node which is going to be deleted can be replaced by in order successor, if we can borrow from the or if we can take from the right child, or if the in order predecessor is available without violating the properties, we can give with the in order predecessor also. In case of the key which was lying on the leaf node, which was our case 1, there were no children. So, there was no point of in order successor and in order predecessor if the key which is to be deleted is lying on the leaf node. Now, this may kind of trigger the what we can say merging of the keys also. So, that we will look with the help of an example, how are we going to do this. So, let us look at this case 2. So, here we have a figure which is I am just again I am concentrating on the part of just the subtree which is of concern to me. So, here we want to delete 33. So, if we want to delete 33, the node which will be the node from which we are deleting will be having 30 only. So, this is perfectly fine to have only one key as far as order of this particular tree is concerned. Here m is equals to 3, but the point is, one particular key in a node cannot have 3 children, because here are 3 children. 25 is 1, then a node with 31 and 32, and then with a node with 35. So, some kind of borrow or something of that sort, or some kind of taking the keys up from the children has to be done, and this can be done only in case of internal nodes. In the case of leaf nodes, you do not have any children, so no point of doing that. So, how are we going to tackle this situation? So, we are talking about the in order successor here, because if I am talking about the in order predecessor, so in order predecessor of that node which is having 30 and 33 is 25, and it is already there on the minimum threshold. So, then in that situation we have taken from the node which is having in order successor, in order successor of whatever node we are left with. So, in order successor of 30 is going to be 32. So, that 32 we are going to take up in the parent node. So, now the parent node is having 2 keys, one is 30, another one is 32. So, with 2 keys in the node, it is perfectly possible to have 3 children. So, left of 30 it is going to be 25, in the middle of 30 and 32 it is going to be 31, and on the right side of 32 it is going to be 35, and this is going to be the situation of your tree after deletion of 33 which lies in an internal node. So, we have taken from the we have taken help from the in order successor of the kind of the tree of the key which is remaining after the kind of we can say remains after the deletion, or even if we look into this other way round, we can say if we are going to delete 33, we have taken the in order predecessor of 33 which is 32. That way is also kind of we can say it is fine. So this was one situation. So the internal node which is deleted is replaced by the in order successor if right child has more than minimum number of keys, but if either child has exactly a minimum number of keys, then we need to merge the left and right children. So, let us see how this is going to happen. So, here in this situation we have two keys in the parent node 30 and 32. Now, let us say we are going to delete 30. Looking into the in order predecessor, we have 25, that means the node which is having in order predecessor is already lying on the minimum threshold. So, that means we cannot carry forward 25 to the parent node or something of that sort. So, what is to be done? We are going to kind of merge the nodes. How this merging is going to happen? So, after let us say after deletion of 30, we are left with only 32 which is available in the parent node, and we have 25, 31, 35. So, 3 children cannot be there. So, we are going to merge 25 and 31, and we are going to put these 25 and 31 on the left side of 32, and obviously on the right side of 32 we already have 35. So, in this way this merger is going to happen, and simply you can merge these keys, and now your key if now your tree, if you look onto, is having perfectly balanced what we can say is the number of children is fine, then number of keys inside the node is also balanced, it is not violating any property anywhere, and also the search property or the search characteristics of the B tree is also kind of we can say preserved. So, it is there. So, this was the case in which we are going to delete the key from an internal node, not from the leaf node, which was the first situation. Now, after merging, let us say this happens that the parent node has less than the minimum number of keys, then what is to be done for? Then we need to look for the siblings as we did in the case 1. So, please recall case 1, we looked for borrowing from the siblings when the underflow situation is occurring. So, till now till this point what we have what all cases we have considered as far as deletion is concerned, we have seen two major situations. One is when the key is lying is on the leaf node. Within that we have seen two situations, one which is triggering an underflow, another one which is not triggering an underflow. Coming to the case 2, we have also seen the case 2 which is the case of when your key which is to be deleted is present in an internal node. So, internal node I am talking about, then that internal node will in case of an underflow, obviously no, not in case of not in the case of underflow, it will definitely borrow from the we can say in order predecessor or in order successor in order to maintain the balance between the number of keys and the number of children. Also, we need to borrow very carefully, we can say, because search property of the B tree is also to be kind of preserved. So, these were actually two cases of the deletion. Now, there comes a third case of deletion in which the height of the tree is shrinking. Now, please recall the corresponding case of the insertion when there was a increase in height of the tree as a result of insertion of one key, because all the keys are actually kind of filled at the last level, and then it is going to increase the height of the tree. Corresponding to that case, here in situation of the deletion, we have the case where case 3 in which the height of the tree is going to shrink. Now, how this height of tree is going to shrink, what is the situation? So, if the target key lies in an internal node and the deletion of the key leads to a fewer number of keys in the node, fewer number as in obviously less than the minimum required. Then look for the in order predecessor or and the in order successor. So, if both the children contain a minimum number of keys, then borrowing cannot take place. This is going to lead to the third subcase of the case 2, which is about merging the children, and that case we have already seen, because neither of nodes, neither the successor in order successor or the in order predecessor was in a situation to lend one key. So, kind of we have seen that merging of the nodes happen. Now again look for the sibling to borrow a key, but if the sibling also has only a minimum number of keys, then we need to merge the node with the sibling along with the parent. Now and obviously we need to arrange the children accordingly. So, for example, we will be taking an visual example of this. So, I am just reiterating it for better understanding. We need to look for the sibling to borrow a key, but if the sibling also has only a minimum number of keys, then merge the node with the sibling along with the parent and obviously arrange the children accordingly, that is in the increasing order, because we also need to maintain the we can say the search property. Let us try to see this case 3 with the help of an example. So, here we have a tree with the the tree is very small. So, the root node is 20, to the left it is 10, to the right it is 35, at the next level to the left of 10 we have 5, to the right we have 15, 30 on the left of 35 and 70 on the right of 35. And what is the task? The task is to delete 10. So, now let us say we are going to delete 10, then this will cause in an kind of an underflow situation. Now, the point is it is an internal node. So, either the kind of considering the case 2, we can borrow from left in order successor or in order predecessor. Now, in order successor and in order predecessor are 5 and 15, they both are lying on the minimum threshold. So, they cannot give. So, when they cannot give, we are going to merge the keys, and that is what we did in the if as you can see on the screen in the right side of the figure, the 5 and 15 nodes are actually merged. Now, 5 and 15 are merged, but it is not going to solve the problem. Why? Because we do not have anything in the kind of parent node of 5 and 15. So, when we do not have anything in the parent node of 5 and 15, we are going to merge the root node 20 and the available node on the level of the deletion, which is 35, and the resulting tree, if you can see, is going to be arranged in such a manner that 20 and 35 when merged with are going to give you the parent node 20 and 35. Then we have 35, but that is 5 and 15 on the left of the 20. On the right of 20, if you can see, it is 30, and on the right of 35 it is 70. So, what has actually happened? When we started initially, the tree was having 3 levels, but as we have deleted 10, one level of the tree is actually shrinked, and now we have only 2 levels. So, this was actually the case when we talk about that, yes, the height of the tree is actually shrinking. So, we have seen in our couple of lectures, we are coming to an end of the deletion process of B trees. In order to summarize, we have seen 3 cases of deletion. The first case says the node lies on the left leaf of leaf node, which is the key which is to be deleted lies on the leaf node, causing an underflow, not causing an underflow. We have covered the whole situation. Then the key which is not lying on the leaf node, but it is lying on the internal node. Then also we have covered that the borrowing situation and the underflow situation, we have also seen merging. The third case was about, even after that merging, we need to kind of shrink, or we need to decrease the height of the tree, which we have just seen. So for as far as B trees are concerned, in order to kind of summarize the usage, please recall that we have so many data structures like binary search tree, AVL tree, red brick tree, but they can store only one key in one node. If you have if you have to store a large number of keys, in these situations, height of such red black tree or maybe binary search tree becomes very large, and the access time increases. So in order to access the data in the lesser time on the physical storage media, just such as a hard disk, these B trees are actually the data structure which comes into the picture, and they actually minimizes the number of disk access, and then they are able to kind of we can say they are able to increase the speed of the disk access. They significantly the height of these kinds of trees, because of the high branching factor, is low, and this low height significantly allows faster disk access. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next lecture. Till then, take care. Goodbye.